Welcome to the Explainer. Today we've got a really cool chemical puzzle. It sounds simple enough. Can a liquid that's made of just one type of element, say pure nitrogen, be polar? Now, the short answer is a hard no. But digging into why that is, well, that uncovers the secret to what makes water the absolute cornerstone of life on our planet. All right, let's really get into the weeds with this. On the surface, it just seems like a standard chemistry question. But what we're about to see is that the answer has these massive implications for, well, pretty much why our world works the way it does. So here's the question in black and white. Can a pure liquid made up of identical nitrogen molecules be polar? Now, before we can even begin to answer that, we've got to get on the same page about what polar even means. It's a word we all hear a lot, but what's really going on inside that molecule? So let's set some ground rules here. When a chemist looks at a liquid and says, yep, that's polar, what are they actually talking about? What's the key thing that makes one molecule electrically different from another? The best way to think about it is like a tiny, tiny magnet. See, a polar molecule has this permanent, built-in electrical imbalance. One end is just a little bit negative because it's kind of greedy and it's hogging all the electrons, and that means, of course, the other end is left being a little bit positive. This built-in north and south pole is what scientists call a dipole moment. And believe me, we are absolutely surrounded by polar liquids. You've got your everyday water, hydrogen peroxide, alcohols, and if you just glance at this list, you're going to spot a really critical pattern. Every single one of these molecules is made of at least two different kinds of atoms. And that's a huge clue for us. And that clue, it leads us directly to the most important part of our whole puzzle, what I'm calling the one-element rule. This is the little detail that honestly changes the entire game. Okay, now we are getting right to the heart of the matter. What if the molecule is made of only one type of atom? Chemists have a term for this. They call it a homonuclear molecule. We're talking about things like ozone, O3, or even those really cool crown-shaped sulfur rings, S8. Can they be polar? And the answer is just a definitive, absolute no. It's impossible. And I don't mean we just haven't found one yet. I mean, it's fundamentally impossible based on the laws of chemistry. So why? What's the reason? Okay, here's the fundamental reason. Polarity is all about a molecular tug-of-war over electrons. To get a polar molecule, you need one atom that pulls on those electrons harder than the other one. But think about it. When all the atoms are identical, like in a nitrogen molecule or an ozone molecule, they all have the exact same pulling power. That's what electronegativity is. So the tug-of-war is a perfect stalemate. The electrons are shared perfectly evenly, and you end up with a totally symmetrical charge distribution and a dipole moment of 0. Game over. It's just a fundamental law. But wait a minute. I can hear you thinking, what about molecules with really weird asymmetrical shapes? I mean, surely a bizarre shape could force the electrons into some kind of lopsided pattern and create a little bit of polarity, right? And you know what? That is a fantastic question. Because molecular shape does matter, a lot of the time. This question pushes us past the simple definition and gets us into a really subtle but super important distinction between a local charge and the overall charge of a whole molecule. And here is that subtle distinction in action. The answer is sort of yes and no. On the one hand, yeah, a weirdly shaped molecule like ozone can have these little temporary, localized pockets that are a bit electron-rich, but, and this is the absolute key, the molecule's overall symmetry means those pockets always, perfectly, balance and cancel each other out. The net result across the whole molecule is still 0. There's no permanent, stable dipole, which means the molecule is still, officially, nonpolar. So the absolute closest these single-element molecules ever get to being polar is something called a quadrupole moment. Now, if a normal polar dipole is like a simple bar magnet with one north and one south pole, a quadrupole is, well, it's more like strapping two bar magnets together in opposite directions. It creates this more complex four-pole electrical field. Now, this does allow for some weak interactions between molecules, but let's be super clear. It is absolutely not the same thing as being polar. Okay, so if molecules made of just one element are completely out of the running, let's look at the real contenders. Who actually wins the prize for the most polar liquid? And, more importantly, where does our old friend water fit into all of this? I think the answer is going to surprise you. All right, let's just look at the numbers. When we rank these liquids by their raw dipole moment, which is basically the magnet strength of a single molecule,
Look where water lands. It's not even close to the top. I mean, stuff like hydrogen cyanide is way more polar on a molecule-by-molecule basis. Kind of weird, right? I mean, we all think of water as the polar liquid, but maybe it's not.
And this is where the whole puzzle gets solved. It turns out there are really two different ways to measure polarity. There's the dipole moment, which we've been talking about this whole time, that measures the charge separation in just a single molecule, and in that race, water is just moderate. But then there's the dielectric constant. This measures the bulk liquid's ability to act as a solvent to stabilize ions. And in this category, water isn't just good, it is off the charts exceptional.
So let's dig into that a little more and see how this one distinction makes water, even with its kind of average dipole moment, arguably the most important polar substance on the entire planet.
So again, here's water's dipole moment, 1.85 dB. It's a respectable number for sure. It's what allows for hydrogen bonding. But, it's not a world beater. But this number, this is water's superpower. A dielectric constant of around 80 is just huge. It represents this incredible power for the liquid as a whole to swarm around charged particles, like the sodium and chloride ions in salt, and just rip them apart. This is why we call water the universal solvent. And this really is the perfect way to sum it all up. Water is not the most polar molecule, but it is, by far, the most polar common solvent. It's this perfect storm of a decent dipole moment, its tiny size, and its unique ability to form this incredible three-dimensional hydrogen bonding network. All of that together gives it that enormous dielectric constant. And that is what allows our oceans to dissolve minerals and our blood to carry the very building blocks of life. And so we've come full circle. The very same fundamental, unbreakable rule of chemistry that makes it impossible for something like liquid nitrogen to be polar, well, that's the exact same rule that makes water so uniquely exceptional. To get polarity, you have to have an imbalance. You need that tug of war between different atoms. And it's that beautiful, essential imbalance that gives water its amazing power, making it the perfect solvent for life as we know it.